Good morning, students. So today we are going to discuss a very important topic, integrated rate law or integrated rate equations. Okay, rate law we have studied. So on the basis of that, how can we derive integrated rate law equations? Okay. Now we will be doing it for zero order reaction and for first order reaction. Okay. So first of all, we will start with zero order reaction. Okay, now how to start? See, we are considering a reaction like this where R represents reactants and P represents products. So if this reaction is of first order, then what we can say on the basis of rate law, rate of reaction is equal to rate constant into concentration of R raised to power 0, because it is zero order reaction. Okay, this is rate law. Now when we want to define rate, then rate can be defined as minus dr over dt, where minus dr means decrease in the concentration of reactants and dt means change in time. Okay, so we are combining these two equations and we are getting rate is equal to minus dr by dt is equal to k r raised to power 0. So r raised to power 0 means 1. Okay. So what we are ultimately getting? We are getting minus dr by dt is equal to k. So when we rearrange it, then we will get dr is equal to minus k dt. Okay. Now when we will integrate, then what will the result? Integration of dr is equal to r. Similarly, integration of minus k dt will give, minus k is constant, so minus k will come out, and with respect to t, integration will be t plus I. Now what is I here? I is just like C. It is constant of integration. In general in maths we write C. So here we have written I. So it is having one and same thing. So concentration of R is equal to minus kT plus I. I is constant of integration. Now if we say that time is equal to 0, it means initially what should be the concentration of reactants? It will be termed as initial concentration, and initial concentration is denoted by R naught. So at T equal to 0, R is equal to R naught, where R naught is initial concentration. Now when we put this value in equation number 1, then what we will get? At place of T we have to put 0, at R we have to put R naught. So value of I or constant of integration will be R naught. Now when we put this value, then ultimately we will get the equation concentration of R is equal to minus kT plus R naught. So from this, when we take kT that side and R this side, then it becomes kT is equal to R naught minus R. Okay, or we can say K is equal to R naught minus R over T. Okay. So this is the equation, or we will say this is integrated rate law for zero order reaction. Okay. Now see, this is what we are getting there. We are getting this. Okay. Now when we compare this equation with the equation of straight line, equation of straight line is y is equal to mx plus c. So if we take R, if we take this on y-axis, if we take this on y-axis and t on x-axis, okay, then there will be a straight line having slope minus k and intercept r naught. Okay, so this is what we are saying. Then when we compare this equation with the equation of straight line, we take r on y-axis, we take t on x-axis, then it will be a straight line with intercept r naught and slope minus k. Okay, so here we have plotted this. This is concentration of R and this is time. Now we are getting a straight line and minus k is the slope. Okay, so slope value will be determined from the graph. So we can determine the value of k graphically. Okay, so what relation we have to remember? We have to remember this relation, K is equal to initial concentration minus concentration after time t divided by T. So R naught minus R over T, where what is R? R is the concentration of reactants when T time has passed. Okay, so this is useful for numerical purposes. Now let us take one example, zero order reaction example. Now see, zero order reactions are rare, or we can say very few reactions are there. So it is not a common thing, it is uncommon normally. So let us take one example, the decomposition of gaseous ammonia on a hot platinum surface. So we can represent this reaction like this. So for this balancing purpose, what we will write? We will write 2 times NH3, it gives N2 plus 3H2. Everything is in gaseous state, reactants also, products also. Here we have taken platinum as catalyst and temperature is 1130 Kelvin. Okay, so if we write rate law for this reaction, then we will write like this: rate of reaction is equal to rate constant into active mass of NH3 or molar concentration of NH3 raised to power 0. So it means anything raised to power 0 means 1. So rate of reaction is equal to K. Now in this reaction, platinum metal acts as catalyst. At high pressure, the metal surface gets saturated with gas molecules. So a further change in reaction conditions is unable to alter the amount of ammonia on the surface of catalyst, making rate of the reaction independent of its concentration. Okay, so what has been said, that if something is there in the reaction for which there is no change in concentration with the passage of time, then we say that our rate of reaction is independent of that. Okay, so here what we are saying, that when this decomposition process occurs, then platinum acts as catalyst and it provides the surface for the reaction to occur. Okay, so after some time when we see, then surface of platinum gets saturated. So at this particular stage, when it gets saturated, that time what happens, its concentration, which concentration? Ammonia concentration, it does not change. Okay, so what we can say? We can say that it has become concentration independent of NH3. Okay, so we say that rate of reaction will not depend on concentration of NH3 now. Okay, so we say that it is zero order reaction. Okay, similarly one more reaction is there, thermal decomposition of Hi on gold surface. Here also we will give the same reason. Okay, so these are 2 examples which you have to remember for zero order reaction. Now let us come to first order reaction. Now consider a reaction. This is a reaction A, it gives B. This is a reaction, and we can write it like this: rate of reaction is equal to K into molar concentration of A. Okay, we have written according to rate law. Rate of reaction is equal to rate constant into molar concentration of A. Okay, now when I write this according to its definition, that is called differential form, then what I will write? I will write rate as minus dA over dt. Okay, now we have got this equation. This equation can be rearranged and can be written as this: minus dA is equal to K concentration of A into dt. Okay, now we will bring A this side, we will again rearrange it, then AA factors will be one side and T will be on other side. Okay, now we will integrate it. So after integration, we will get here log A, integration of 1 by x with respect to x is equal to log x. Okay, now here it is natural log. This you have to remember, don't write log. Log is common log. Here we are writing natural log. So it is natural log of A is equal to minus kt plus c. C is again constant of integration. Okay, just like in earlier derivation we got. Okay, now again we will say initially when time is equal to 0, molar concentration is equal to initial concentration. A is equal to A naught. Okay. So we will put this value in this equation, and we will get C value as log of A naught. Now C value also we got, again we will put in this equation, and we will get log A is equal to minus KT plus log of A naught. Now log A naught we will take from right side to left side, and then it will become log A minus log A naught. Log M minus log N is equal to log M over N. So it will be log M over N is equal to minus KT, means M is here A and N is here A naught. So log of A over A naught is equal to minus KT. Okay. Now this can be written as log of A over A naught is equal to minus KT. Now see, don't confuse in this. It means it is the concentration of A after time t, and this means it is the concentration of A at 0 time, means initial concentration. Okay. So in general this is final concentration, this is initial concentration. So we can write just A also, where we have written AT. Okay. So we can write A also. That is understood that it is the concentration after time t. Okay. Now from this equation we can directly write it like this. Okay. Log of x is equal to A. If we have log of x is equal to A, then we can write it like this: x is equal to e raised to power A. Okay. Because when we will take its log, then it will become log x, left side, right side it will be log of e raised to power A. So log m raised to power n is equal to n log m, and log of e is equal to 1. Okay. This log is to the base e. Okay. We can write log to the base e, or we can write simply ln. Okay. So it is ln, natural log. Natural log of e is equal to 1. Okay. Now this has changed in this form. Okay. And this form is called integrated form of the first order reaction. So sometime we are asked that derive the integrated form of first order reaction. Then this is the form we have to derive till this point. Okay. Now since we are determining graphically, so now let us go ahead. Now see, this thing can be written as this. What we did now? We converted natural log into common log. Natural log of x is equal to 2.303 common log of x. Okay. So here what is x? X is A over A naught. Okay. So log of A over A naught, natural log of A over A naught is equal to 2.303 times common log of A over A naught. Okay. So we have changed this into this form. Okay. So 2.303 into natural log of A over A naught is equal to minus KT. Now when we change this, when A over A naught is written like A naught over A, then we have to change the sign also. Okay. So minus KT changes to KT if I reverse this. Okay. Now whatever we are getting here, that can be rearranged in this form. K is equal to, I will bring T this side, then it will become 2.303 over T log of A naught over A. Now this is the very much important reaction which is required for numericals. Now what is there? This is rate constant, this is initial concentration, this is concentration after time t. Okay. Now one more thing, very important thing, sometime we are given that 10% of the reaction is complete. That time this reaction can be changed in this reaction. Now what does it mean? It means A is 100 here and X is percentage completion, percentage completed. Okay. Now see, suppose our question is that 10% of the reaction is complete, then it means A is 100, X is 10. So A minus X will be 90. Okay, so this is you have to remember. So this can be changed into this form if percentage is given, and if we are given exact values that this much is the initial concentration, this much is the final concentration, then we can use directly this form. Okay, so this is for numerical purposes. Now we can write this equation like this. Okay, log m over n is equal to log m minus log n. Now when we arrange this equation, then it can be written like this. Now let us compare. This is y and this is on x-axis. When we are comparing with equation of straight line, then what we find? If I plot a graph between log a versus t, okay, then I will be getting a straight line having a slope minus k and intercept log of a naught. Okay, now let us see here. See, here R is reactant, concentration of reactant. So we have plotted the graph between log of R and T. Okay, so we got the slope as minus k. Okay, slope is minus k and intercept is log of R naught. Okay, now if I take log of R naught over R versus T, then intercept value becomes 0 and slope becomes this. Okay, slope becomes k by 2.303 and intercept value becomes 0, and so this is the graph which we will get. Now here one thing you can remember, if slope has negative value, then straight line, you have to draw a straight line, but how to draw, this way or this way? When our slope value is negative, then we have to draw this way. Okay, when slope value is positive, then we have to draw this way. So this is what you can remember. Okay, now let us solve this example. The initial concentration of N2O5 in the following first order reaction. This is first order reaction given to us, and initial concentration is given this. Okay, the concentration of N2O5 after 60 minutes means change in time, or time value is given, it is 60 minutes. Okay, and the concentration is found to be this much, 0.20 into 10 raised to power minus 2 mole per liter. Okay, now see, we are given initial concentration also, we are given final concentration also, and we need to calculate the value of K. So we apply this formula. This is one and same thing. See what we are applying. We are applying K is equal to 2.303 over T log of initial concentration over final concentration. Okay, this is what we are applying. So don't confuse in this form. So see, this is there. So 2.303 is there. T value we have taken 60 minutes. Initial concentration is given. Final concentration is given. So first of all, we will solve this exactly properly. So we are getting this much. Now log of 6.2. Okay, how to calculate log and anti-log, this I have given you one video, you might have seen that, so you might be knowing now that how to calculate the log and anti-log values. So from the log table you will find the value of log 6.2 and then you will put the value, and after multiplication you will get the value of K as this much. Units are always those units which are given to us. Now since we are dealing with first order reaction, and for first order reaction, what are the units of K? Units of K are time inverse. If time is in second, then second inverse. If it is in minutes, then it is minute inverse. Same way, whatever is the time, that way we have to write. Now whatever we have discussed about zero order reaction and about first order reaction, you have to solve these home assignments. Okay, thank you.